Okay, next section in chapter 13, we're starting off with vector fields. So kind of like chapter 12 ended with kind of a weird little section, chapter 13 begins with a weird little section, and it's actually weird in a good way. It's a pretty easy little section here, hopefully for you guys. So let's give it a go here. We got vector fields. So you have seen something very similar to vector fields before called slope fields, okay, that we did in calculus, AP Calc. Vector fields are like slope fields, and that they show like a direction. But they also, okay, if it's a vector field, they're going to show direction and magnitude. Okay. Sometimes that magnitude is shown by darkness, darker in color. That's a possibility. More often, you're going to see them as longer for higher magnitude. But if you think about it, if something were to get, too long in magnitude, it might get too confusing in the field that you're looking at. So that darker in color might make more sense. Okay. So we might look at an example of a vector field as being something like, let's see here. Let's do, I like all my different colors. Let's see. Okay, something like, this is maybe our vector field. Okay, and you can see that this shows counterclockwise motion, but also shows stronger or faster as you move outward. Okay, this could be wind speed. Water current. Oh, I spilled water like that. Water current, etc. Okay, and then just like I said too, maybe we would show that with darker color, which again, you're not going to see that much, but let's see what I think my yellows might be the best here, where maybe it looks like that, and then like that, and then like, is it a little darker? I guess it is. Maybe. Okay, where I'm trying not to make them at any different length, but like as it gets darker, you could think that those are the ones with the higher magnitude. Okay. They can also occur in 3 dimensions. Okay, so it's easier to draw them in 2 dimensions, but they can also occur in 3 dimensions. So we're going to look at 2 examples. First example, I think this is exercise 2 in your book, unless it's actually example 2. I think it's exercise. Okay, but we are supposed to sketch the vector field. Okay, that's the notation that we're going to use. 1/2 x in the I direction, and then y in the j direction. And I think when your book makes a table, it always bothers me how they make it. I guess your book doesn't do it that different. Sometimes when books do slope fields, the way they organize their table doesn't make sense to me. So I like to organize my table just like I would in the coordinate plane. So it's my brain just copies it over easier. So I put x values across the top, smallest to largest. I'm going to run out of room if I make it too little here. It's going to be kind of obnoxious if I make it too big here, but it's okay. Okay, so those are x values. and then y values to, whoops, +1, 0, -1, -2. And then I can just kind of copy it right over onto my plane. Okay. So when I'm at the x-coordinate, -2, and y-coordinate +2, my vector, let's see, it'll be 1/2 x, so -1, and then it'll be y. Okay, so at the point -2, 2, I'm going to draw that vector. And then, and it's, sure, I'm going to fill in 25 values right now, but they definitely kind of follow a pattern here. So all of these are going to be 1/2 x and then y. Okay, and then -1/2, 2. Okay, and then these are all going to be 0, and then the y's. Okay, and then 1/2. And then the y's. And almost done. Now I'm going to have 1, and then the y's. Okay. So now there's my table of values. Now I just have to actually sketch the vector field. So do this. Let's see, 0, 1, 2. -1, -2. Okay, so I've got my points. So I'm going to sketch the vector field at these 25 points. All right, get a different color here. Okay, so at the upper right hand, I need to go, I need to have a slope of down, sorry. Let's see, in the x direction, -1, and the y direction, +2. So if I do it to scale, it's actually going to look like this. And I believe that's the way your book does it. They try to keep it to scale like that, which is, again, where you get kind of messy. But let's hope that this one doesn't get too bad. Okay. So, like, again, for example, the one that I just drew, that one is the vector -1, -2. Okay, so in the x direction, I start at the point, and then I move to the left -1, or to the left 1, down 2. Okay. Now I'm going to do my next column where I'm going to move left 1/2, and then up 2. Left 1/2, and then up 1. Okay. Left 1/2, up 0. Left 1/2, down 1. Left 1/2, down 2. Roughly. Okay. Now all of these next ones are just straight up or down. So up 2, up 1, up 0, down 1, and down 2. Okay. And then I'm going to have some symmetry here, right? So right 1/2, up 2, right 1/2, up 1, right 1/2. Okay, and then finally, like that. Okay, that's what my vector field would look like. Okay, we are going to attempt a 3D one, which can get real messy, but you're gonna give them a shot at least, right? It's so good for your brain to try to think spatially like this, but it's also very frustrating. But let's give it a shot. The 3D ones, they don't make them as complex as the 2D ones. This one is just your vector field is negative y in the k direction. Okay. Now what that means is whatever point you're at, you move down because that's a k, right? Whatever your y coordinate is. Okay. So let's give this a shot. Man. And we're not even going to make the table for this. We're just going to kind of sketch some in and try to make this nice and big and not too busy, I hope. And, maybe you can just picture some of them. Okay. Like obviously at 0, 0, 0, you're just going to have a dot, right? I'm going to draw in some grid lines here. Let's do like a highlighter light. Oh, I don't want to use green though. Let me do pink. Maybe so that the green contrasts with it enough. So like kind of a grid along the floor here, including the negative ones. Okay. Okay. So what I tried to do here is these are just in the XY plane. Okay. So now along my x-axis, y is 0. So these are all just going to be dots here. Okay. All of these points have a y coordinate of 0. All right. Now, if I move over to the next kind of pinkish line where y would be 1, then I'm going to point down with a magnitude of 1. So these are all going to be pointing down with the magnitude of 1. And you don't have to stick to whole numbers. It's just obviously we want to. It's easier. But I could just as easily go to 1/2 and just do a little guy there pointing down. That's half the distance. Anywhere along that line, really, right? I could draw the ones all along here if I want to. Okay, but those are just all along where y is 1. All right. I should probably put another one in there. Okay. Now my next one is when y is 2, so I'd make those twice as long as the ones. As best I can, right? Okay. Just so you're getting an idea of what's going on here. Okay. And then the farther I go out, the more they're going to point down. Okay. Then if I go to the left, I'd be pointing up at 1. Okay. And you can almost picture like a 3-dimensional shape being made here, right? If I were to fill all of these in, okay, what I would have going on is kind of like this little, well, it's like a plane like that. If I had to cut it off, yeah, it kind of looks like that, right? But these guys would actually keep going up. Did I just do that right? Yeah, and then you'd have like a cutoff there. And it kind of looks like that. Like if you were to look at it from the side, like these are all your arrows pointing up, and these are all your arrows pointing down. You can kind of picture almost like it's a solid. But the bad news is that that's only when z is 0, okay? Only when we're in the xy plane. So then you have to think about too, well, if I were, the next layer on top of that, right? If I were at like z is 1, I'm going to have the same thing, okay? So no matter where I am, let's see here. You can try to draw it like when z is 1. Okay, if I'm at like the next level up, oops, I meant to do a highlighter there. Okay, so like we were on the first floor, now we're on the second floor. Okay, where z is 1, and the same thing, right? When z is 1, still over here, when y is -2, these guys are pointing up too. Okay, and still over here, these guys would be pointing down. So what you really have is like a wall of arrows, this arrow being directly above the other one. Kind of have this wall of arrows. Okay, just try your best again to visualize it and think about what it means too. It means as we move further along the y-axis, whatever this is getting stronger. Okay, and it's not dependent all on x or z. All right, you could try to draw, I think in my notes, what I must have done in class before is try to draw like an actual cube where I had maybe something like but then also came out from that. It's like a little 2x2 Rubik's Cube kind of thing, and tried to draw it at each of the little intersections there, and that gets pretty messy too. So yeah, 3D, not always very easy, but we give it a shot. Okay. Then the only thing we have to add to this, like that's the basic idea here. We're going to add what's called gradient vector fields. So where we would draw in the gradients. Okay. So your gradient in any direction. Okay, so your partial in x, whatever that is a function of x, y. Oh, you know what? I think they don't have a z on this one. I think they give it to you in 2D first. Yeah. Get rid of that z there. Then they do explain it, that it can be 3D also. But boy, you don't want to draw these in 3D. So your partial in y. Okay, so we would just like draw all of the gradients. Okay, so we've done gradients before. It's nothing new here, but just the whole idea of drawing, a whole collection of gradients. Okay, and again, like I said, you can do this in 3D too. You just have one more term. Okay, we do something like that. Okay, a couple things here when you draw in, and we know this before too, gradient vectors. Gradient vectors are perpendicular to level curves. Okay, so we're going from drawing like one curve or one surface and figuring out its gradient at a single point to thinking about a whole family of level curves and drawing in the gradient vector field. Okay, and it's kind of an interesting thing to look at. So you already know that gradients are perpendicular to the surface or the curve. Gradient vectors are long when level curves are close. Okay. to each other. And then we can kind of rewrite the same statement. They're short when level curves are far from each other. Okay, we're going to look at exercise 25, I think, is find the gradient vector field. Yeah, okay. So example 25, I'm going to kind of look at this a little bit and get some properties of these fields figured out. Fxy equals x squared minus y. We're going to find the gradient vector field. And we're also going to look a little bit closer at this. It doesn't say so in the instructions, but we're also going to draw in some level curves too, and just kind of see how those properties are shaken out, just because it's fun. Okay, so first of all, your gradient vector field, okay, will be your partial in x. So it's going to be 2x in the I direction. And then your partial in y, so -1 in the j direction. Okay, so again, we can draw in some of these values here. I'm going to skip the table on this one. I think we still, let's see, in my notes, 1, 2, 3, 4, 5, 6. We're not going to draw on this many. It's just more to get the whole scaling because of the magnitude. Okay, so at 0, 0, we will have 0, -1. Okay, and in fact, when x is 0, we will always have 0, -1. So all of these guys be right here. Oops. They all are 0, -1. I think I'm doing the best I can. And again, remember, you don't have to just start at a whole number, just kind of we always do. Okay, just because it's easier to draw. When x is 1, then we will always have 2, -1. Okay, so when x is 1, we're going to go over 2 and down 1. So that's what those are all going to look like. When x is 1, we'll go over 2 and down 1. Okay, when x is 3, we're going to have 3, -1. So we'll always go, and now we're going to kind of overlap here, right? Oh, I don't know why I skipped 2. 2, it'll be 4, -1, that's why. Okay, so when x is 2, we'll go over 4, 1, 2, 3, 4, and down 1. Okay, so those are going to look a little bit like that. Okay, and I'm trying to start like, the next one I'm going to do is at the point 2, 2. Doing my best here. Maybe I need a ruler or something. Okay, kind of like that. All right, then we do the same thing with the negatives. All right, when x is -1, then we'll have, oops, -1, -2, -1. Keep on forgetting to multiply it by 2 like we're supposed to. Okay, so -1, I'm going to go left 2 and down 1. Okay, those are going to look kind of like that. I'm going to start to get a little messy here. Okay, and then at -2, we're going to have -4, -1. Okay, so 1, 2, 3, 4. Those are all going to look somewhat like that. Okay. All right, so that's your gradient vector field, which is great. But if we can draw in some level curves here also, that's going to get more interesting. Okay, and like I said, it didn't specifically ask for it, but we're going to take a look here. So fxy equals x squared minus y. So remember your level curves, you make the value of a function a constant. Okay, I'm going to rearrange this. Y is x squared minus k. Okay, so we can see that this family of curves is all parabolas that are shifted by whatever amount. Okay, so your level curve when k equals 0 is going to be your parabola, just your basic parent function parabola. Looks like this. Okay, then when k is 1, we shift it down 1. Okay. Oops. Trying to get that drawn in as best I can. All right. If k is -1, then shift it up 1 actually. Okay, so we can start to kind of get those in. And just like what we were saying, first of all, remember those two properties. Your gradient vectors are perpendicular to the level curves, which it appears that they are. We can also prove it pretty easily. Okay, y prime is 2x. Okay, and over here, your slopes, here, I guess I should do this. Your slopes would be the change in y over the change in x. That looks like an opposite reciprocal to me. Okay, so at any point you could find on these parabolas that the gradient is perpendicular to it. All right, and then our second part there too, that they're longer when our level curves are close to each other and shorter when they're farther away. Okay, the shortest, let me change the color here. My shortest gradients are right there going through all the vertices where they're the farthest apart, that family of curves are, and they get closer together at the tails, and that's where those gradients also get to be higher in magnitude. Okay, all right, and that's it for 13.1. So nice little short one for you guys.